Now in section 10.5, you have plenty of examples to calculate directional derivatives with your new knowledge that show you how easy it is actually to calculate them. For example number 1, you're told to calculate the directional derivative. This is du f of x, y, z along a direction given by the vector v with components -1, 0, 3. And the function, in this case, f of x, y, z, is given by x to the power of 2, z plus y to the power of 3, z squared minus x, y, z. And you can see this in the lecture notes in case this is a little bit too small. And I'll go through all the steps so that it's absolutely clear. Remember that for this week you will not be assessed in the worksheet, but this is all examinable material, and therefore you should really be comfortable doing all these examples and problems. In order to calculate directional derivatives, the first step is always to calculate the unit vector. The unit vector in this case is just given by v divided by its modulus. In this case, you can calculate its modulus or magnitude, square root -1 squared plus 0 squared plus 3 squared. In this case, you end up with square root of 10, and therefore the unit vector is given by -1 over square root of 10, 0, 3 over square root of 10. These are components A, B, C. Step number 1 is usually very easy, but please do not forget you need to calculate the unit vector. If you don't do that and you use these components directly, you're not really getting the directional derivative. The next step, step number 2, is you need to calculate the partial derivatives. fx, in this case, should be just 2xz. There is no dependence on x here, and there's a dependence there that's minus yz. fy, there is no dependence on y, but there is here. You get 3y squared z squared minus xz. And finally, for z, we get x squared plus 2y to the power of 3z minus xy. These are the 3 partial derivatives, which are the key ingredients for the directional derivative. The final steps include understanding or knowing what you need to actually plug in. Remember that the directional derivative, as we've shown, can be essentially written by fx a plus fy b plus fz c at specific points. In this case, we want to keep it general, so all we have to do is to plug in the values. In this case, this would be 2xz minus yz multiplied by -1 over square root of 10. There's a great thing happening, which is component b is actually 0, therefore this component vanishes, and we're left with fz, that's x squared plus 2y cubed z minus xy, which is being multiplied by 3 over square root of 10. And you can further simplify this. You can also take out the 1 over square root of 10, which will be affecting everything. And you can also put it just like we have in the lecture notes. We have the 3 here, it's multiplied by x squared plus 2y cubed z minus xy. And then we have minus 2xz minus yz. And you can also have square root of 10 over here or outside, but this would be your final answer. The directional derivative along vector with components -1, 0, 3, corresponding to unit vector with components -1 over square root of 10, 0, 3 over square root of 10 of this specific function is this. In some cases, like you have in the lecture notes, you would be calculating a directional derivative, not just in general, but sometimes for a specific point x, y, z equals some x0, y0, z0. In this case, all you have to do is you then plug in where you have x, you'll be plugging in x0, where you have y, y0, and etc. And that will give you an actual number. You should really attempt all the questions in this week's worksheet about directional derivatives, for which the solutions are fully available, so you can mark yourself and pinpoint anything that is not clear. But there is one kind of problem which I really want to show you how to do, so that if you find them, you don't struggle or get scared. And this is, for example, using polar coordinates to define the direction of a vector. You'll find this as example number 2 in your lecture notes in 10.5. In this case, we want to calculate the directional derivative along a unit vector u for the function at a specific point. This is what it means. It means at a point xy given by 2, 0. We want a number at the end. In this case, the function f xy is given by x e to the power of x y plus y. This is the function. And the subtlety is that the direction here is not explicitly given as a vector, but either as a direction in polar coordinates, which is theta equals 2/3 of pi. Now the first thing, as in the previous example, what you need to do is to calculate the unit vector. In this case, you're not really given a vector, but actually a direction in polar coordinates. So it's probably a very good idea to remember the coordinate transformations and components x, y are cos theta, r sine theta. In this case, if you're told calculate along a direction given by an angle, what you're really trying to do is you're calculating components A and components B on the axis. One thing you could ask then is, okay, so if this is polar coordinates, there's r and theta. So what is r? In this case, you know that r has to be 1, because by definition, the modulus of the unit vector is 1. And for polar coordinates, that's what you actually need. Therefore, calculating this is all about A is simply 1, that's because it's the radius, times cos of 2 pi over 3, and B will be 1 times sine of 2 pi over 3. In this case, component A is minus 1.5, and component B is square root of 3 over 2. This completes step number 1, which is slightly different, but it is good to be aware that all you're doing is also using your understanding of polar coordinates and what r really is to get the unit vector as minus 1.5 square root of 3 over 2. If you want, you'll see that the sum of the squares and the square root would give you 1. Since we have this, let's get rid of this part. It's better. And we can go to step number 2, which is now much more easy. All we're doing is calculating the partial derivatives in respect to x. In this case, we're looking at e xy plus the derivative, the chain rule, y x e xy. And for the partial derivative in respect to y, in this case, we get x squared e xy plus 1. Once you get to this stage, because we want it at a specific point, we can already calculate. In this case, we end up with e to the power of 0. This will be 1 plus 0. And in this case, we end up with 2 to the power of 2, e to the power of 0 plus 1. And this is simply 4 plus 1 equals 5. The directional derivative is therefore d u f of 2, 0 is given by fx at 2, 0, which is 1 times minus 1.5 plus 5 times square root of 3 over 2. And if you really care that much, you can also just write it something like 5 square root of 3 minus 1 over square root of 2. And this would be your final answer. The only subtlety, the difference is, in this case, you were given the direction with an angle. You need to make sure that you convert it into coordinates a, b. And also the other difference is that you're calculating it for a specific point. And this implies you're looking at a numerical answer at the end, but it's more than okay to leave things with rational numbers, square roots, or e. You don't need to then give an approximate answer. This would be fine, and it would be your final answer.